In a three-phase delta system with a high leg, a ground fault occurs when one of the three phases makes contact with the ground. This fault creates an unbalanced current flow that can result in overvoltages and other hazardous conditions. A high leg is a neutral point created by connecting a transformer in a special configuration. This point is typically rated at a voltage that is 1.732 times higher than the phase voltage. In this instance, the phase voltage is 208 volts, so the high leg is rated at 208 volts times 1.732, which equals 360 volts. When a ground fault occurs, the voltage readings between the phases and ground can become unbalanced. The readings observed may show at a ground at 743 volts, which is higher than the high leg, B to ground at 915 volts, which is even higher than the high leg, and C to ground at 762 volts, which is still higher than the high leg. The high voltage readings on the B and C phases are due to the fault current flowing through the ground. This fault current creates a voltage drop in the neutral path, which is why the phase voltage to ground is lower than the readings on B and C. According to the utility, it is acceptable to have high voltage readings in the grounded phases B and C under certain conditions. These conditions may include: firstly, the fault current is limited by a protective device such as a fuse or circuit breaker. Secondly, the system is properly grounded, meaning the ground electrodes have a low impedance to earth. And thirdly, the system is not connected to a susceptible load that can be damaged by overvoltages. While it may be acceptable in some cases, a ground fault can still be hazardous and needs to be addressed. Some safety precautions to take are: firstly, disconnect the affected circuit and lock out or tag out the equipment, and secondly, call a qualified electrician to investigate and repair the fault, and thirdly, ensure that the system is properly grounded and protected. Understanding the nuances of a three-phase delta system with a high leg, particularly concerning ground faults, requires a deeper dive into the system's configuration, voltage behavior, and safety measures. The delta configuration, unlike a Y configuration, does not inherently provide a neutral point. The high leg, also known as the stinger leg or wild leg, is created through a specific transformer winding arrangement. This arrangement allows for the availability of both three-phase power and single-phase power from the same transformer bank. The high leg is typically identified by its orange color coding. It is crucial to understand that the voltage from the high leg to the neutral point is significantly higher than the voltage from either of the other two phases to the neutral point. This voltage difference is what necessitates careful attention when dealing with this type of system. The presence of a ground fault introduces complexities in voltage measurements and current flow. When a ground fault occurs, current finds an unintended path to ground. This can be due to insulation failure, accidental contact, or other unforeseen circumstances. The fault current flows through the grounding system, potentially causing voltage drops and imbalances. The readings of 743 volts, 915 volts, and 762 volts from phases A, B, and C to ground respectively indicate a significant ground fault condition. These elevated voltage readings are not normal and warrant immediate investigation. The utilities statement that these readings are acceptable under certain conditions requires further scrutiny. It is essential to understand the specific parameters and protective measures they are referencing. The acceptability of high voltage readings during a ground fault hinges on several factors. Firstly, the presence and effectiveness of overcurrent protection devices such as fuses and circuit breakers are paramount. These devices must be properly sized and coordinated to quickly interrupt the fault current, minimizing the duration and magnitude of the overvoltage. Secondly, the integrity of the grounding system is critical. A low-impedance ground path is essential to facilitate the flow of fault current back to the source, enabling the overcurrent protection devices to operate effectively. The grounding system should comply with applicable electrical codes and standards, such as those outlined in the National Electrical Code (NEC). Thirdly, the sensitivity of connected equipment to overvoltages must be considered. Some equipment may be more susceptible to damage from even brief overvoltage conditions. If sensitive equipment is present, additional protection measures such as surge suppressors or isolation transformers may be necessary. It is essential to verify that the utility's assessment of acceptability is based on a comprehensive evaluation of these factors. The fact that the phase voltage to ground is lower than the high leg voltage suggests that the fault is affecting the voltage distribution within the system. The fault current is causing a voltage drop in the ground path, which reduces the voltage reading on the phase. This phenomenon highlights the importance of understanding the behavior of fault currents in this type of system. Addressing a ground fault in a three-phase delta high leg system requires a systematic approach. The following steps should be taken. Firstly, disconnect the affected circuit and implement lockout/tag-up procedures to ensure that the circuit remains energized during the investigation and repair. Secondly, visually inspect the circuit for any signs of damage, such as burned insulation, loose connections, or physical contact with grounded surfaces. Thirdly, use a multimeter or other appropriate test equipment to verify the presence of a ground fault. Measure the resistance between each phase conductor and ground. A lower resistance reading indicates a ground fault. Fourthly, systematically isolate portions of the circuit to pinpoint the location of the fault. This can be done by disconnecting loads, opening switches, or removing sections of wiring. Fifthly, once the fault has been located, repair or replace the damaged components. Ensure that all repairs are made in accordance with applicable electrical codes and standards. Sixthly, after the repairs have been completed, thoroughly test the circuit to verify that the ground fault has been cleared and that the system is operating normally. Measure the voltage between each phase conductor and ground to confirm that the voltages are balanced and within acceptable limits. Seventhly, document all findings, repairs, and test results. This documentation will be valuable for future troubleshooting and maintenance. In addition to these steps, it is important to consult with a qualified electrician or electrical engineer who has experience with three-phase delta high leg systems. These professionals can provide valuable insights and guidance. They can also help ensure that all safety precautions are followed and that the repairs are performed correctly. The NEC contains specific requirements for grounding and bonding in electrical systems. These requirements are designed to minimize the risk of electric shock and fire. It is essential to comply with these requirements when working on a three-phase delta high leg system. Some key NEC articles related to grounding and bonding include Article 250, which covers the general requirements for grounding and bonding, Article 250.24, which addresses grounding of service-supplied alternating current systems, and Article 250.30, which pertains to grounding separately derived alternating current systems. Understanding and applying these NEC requirements is crucial for ensuring the safety and reliability of the electrical system. The utility's role in addressing ground faults is also important. Utilities are responsible for maintaining the integrity of their distribution systems. They may have specific procedures for responding to ground faults and for coordinating with customers to resolve these issues. It is important to communicate with the utility and to follow their guidance when dealing with a ground fault on a three-phase delta high leg system. Furthermore, consider the long-term implications of operating an electrical system with a known ground fault. While the utility may deem certain voltage readings acceptable under specific conditions, prolonged operation with a ground fault can lead to additional problems. These problems may include increased stress on electrical components, reduced equipment lifespan, and a higher risk of electrical hazards. It is generally advisable to address ground faults as soon as they are detected, even if they do not immediately pose a significant safety risk. Proactive maintenance and repair can prevent more serious problems from developing over time. In conclusion, dealing with a ground fault on a three-phase delta high leg system requires a thorough understanding of the system's configuration, voltage behavior, and safety measures. The elevated voltage readings observed indicate a significant fault condition that warrants immediate investigation. While the utility may have specific criteria for acceptability, it is essential to consider all relevant factors, including the presence of overcurrent protection devices, the integrity of the grounding system, and the sensitivity of connected equipment. Following a systematic approach to troubleshooting and repair, consulting with qualified professionals, and complying with applicable electrical codes and standards are crucial for ensuring the safety and reliability of the electrical system. Remember that electrical work can be dangerous. Always follow proper safety procedures and seek the assistance of qualified professionals when necessary. A three-phase delta system with a high leg presents unique challenges and requires specialized knowledge. Taking the time to understand the intricacies of this system and to address ground faults promptly and effectively will help ensure the safety and reliability of the electrical system for years to come. Considering the application of a high-resistance grounding system can be beneficial in mitigating the impact of ground faults in a three-phase delta system. High-resistance grounding limits the fault current to a low level, typically around 5 to 10 amps. This reduces the risk of arc, flash, and other hazards associated with high-current ground faults. It also allows the system to continue operating during a ground fault, as the fault current is not sufficient to trip over current protection devices. High-resistance grounding requires the installation of a resistor between the neutral point of the transformer and ground. The value of the resistor is chosen to limit the fault current to the desired level. While high-resistance grounding can offer significant advantages, it is important to carefully consider suitability for a particular application. It is not appropriate for all systems and may require modifications to existing protection schemes. Furthermore, regular monitoring of the grounding system is necessary to ensure that the resistor is functioning properly. Another important aspect to consider is the coordination of overcurrent protection devices. In a three-phase delta high leg system, the presence of the high leg can affect the performance of overcurrent protection devices. The high leg has a higher voltage to ground than the other two phases, which can result in different fault current levels. It is important to properly size and coordinate overcurrent protection devices to ensure that they will operate correctly under all fault conditions. This may require the use of specialized fuses or circuit breakers that are designed for use in three-phase delta high leg systems. Additionally, the use of ground fault protection equipment can enhance the safety and reliability of the system. Ground fault protection equipment is designed to detect lower-level ground faults that may not be detected by conventional overcurrent protection devices. This equipment can trip a circuit breaker or sound an alarm to alert personnel to the presence of a ground fault. Ground fault protection is particularly important in systems that serve sensitive loads or that are located in hazardous environment. It is also important to regularly inspect and maintain the electrical system. This includes inspecting wiring, connections, and equipment for signs of damage or deterioration. It also includes testing overcurrent protection devices and ground fault protection equipment to ensure that they are functioning properly. Regular maintenance can help to prevent ground faults and other electrical problems.